All right, so have you ever really thought about this? Like when your computer is just completely slammed, you're doing something intense like rendering a video or you're in the middle of some huge game and you see the CPU is maxed out. But it doesn't just like totally freeze up, right? You can usually still move the mouse around, maybe even switch to a different window. So like what's the trick? What keeps things running even somewhat smoothly when it seems like it should be totally bogged down?
Yeah, it's a pretty amazing thing when you think about it. I mean, it's fascinating how the operating system can keep things at least somewhat responsive for you, even when the CPU is going full tilt. And, well, that's exactly what we're going to try to understand today.
Exactly. We're going deep on the CPU scheduler. Think of it as like the brain behind how your CPU works. It's this fundamental part of every operating system. And it's the thing that gets to decide which tasks actually get to use the CPU at any given time. So what we're going to do today is we're going to try to figure out how it juggles all these different things it has to do, and especially how it makes sure things stay smooth for you, even when the whole system is under a ton of stress. Like how come those interactive things, like when you click something, how come that still usually works, even when the computer's super busy?
And to add to that, the smooth experience, it's not just some happy accident. This is the result of a lot of really clever engineering and these super smart algorithms that have been developed over like decades of work on operating systems. So what we're going to talk about today is based on some really cool technical stuff that goes into how these different algorithms work. And, companies like Stonefly.com, they really understand these core ideas and they use this knowledge to build super high performance solutions.
That's right. And speaking of high performance, this deep dive is brought to you by Stonefly.com. They're a leading solutions company, and they have a really strong grasp of how to make systems perform at their best, even in those crazy, complicated situations where things get really demanding.
So getting down to it, what CPU scheduling really means is it's how the operating system decides which task, or more technically, which process gets to use the CPU at any given time. Now, the big idea isn't just to make sure the CPU is busy, although that's definitely important for efficiency. We call that CPU utilization. But it's also about making sure that the system actually feels responsive to you, the person using it. Of course, things like throughput, which means how many tasks actually finish, or turnaround time, which is like how long a whole task takes from start to finish. And waiting time, all these things matter. But, for you, sitting there at the computer, it's that split-second response when you click or type something. That's what really makes it feel smooth, right?
Okay, so let's zoom in a bit. When a program's running, what does it actually mean for that program or that process, like we're calling it, to actually use the CPU? Like, what's really happening down there?
So picture this. When you open a program, your operating system sets aside a chunk of memory just for it. And inside that memory, there's a section called the text section. That's where the actual instructions live, the code that makes the program do its thing. Now, the CPU itself has this special register, kind of like its attention span, called the address register, or sometimes the program counter. It basically keeps track of what instruction the CPU should be looking at next. So when the operating system decides to give the CPU to a particular process, what it's doing is telling that address register, hey, go look at the beginning of this process's text section. That's how the CPU knows which instructions to start fetching and running for that program. This basic understanding of how processes work with the CPU, it's fundamental for getting the best performance out of a system, and it's something that solution companies like Stonefly.com, they really get.
So it's kind of like directing the CPU's focus to a specific set of instructions, right?
You got it. It's like shining a spotlight on the code that needs to be run. Now, when the CPU has to switch its attention to a different process, the operating system does something called a context switch. And it's not just a simple swap. The system has to carefully save everything about the process that was running, where it was in the code, the values it was using, all that, so it can come back to it later without missing a beat. Then it loads up all the saved stuff from the next process that's about to get its turn. Efficiently managing and switching between these process states, it's a specialty of companies like Stonefly.com, especially when they're building really reliable systems.
Okay, so we have all this saved state information, but where does it actually go?
Right, so that brings us to something called the process control block, or the PCB. Now, you have to remember, a process isn't really a physical thing like a file on your hard drive. It's more like a snapshot of what a program's doing at a particular moment, like kind of context for what's happening on the computer. And the PCB is how the operating system keeps track of all these snapshots. Think of it as a detailed record for each program that's running. It holds everything important, whether it's currently running or waiting for something or was in the code, all its internal values and other bookkeeping stuff. Every time a new process starts, the OS immediately makes a PCB just for it. And this PCB, this little record, is what the operating system uses to make all those scheduling decisions. And believe me, efficiently handling all those PCBs, that's super important for making the whole system run smoothly, and it's something the experts at stonefly.com are very aware of.
Okay, so we got these PCBs, these little records. So the simplest way to decide who gets the CPU next, it seems like it would just be whoever asked first, right? Like standing in a line, first come, first served.
Exactly. First come, first serve, or FCFS, is like the most basic CPU scheduling algorithm. The idea is simple. The first process that asks for the CPU, it gets it, and it keeps it until it's completely finished. And the way it's usually done is with a first in, first out queue, a FIFO queue. So when a process is ready to go, its PCB goes to the back of the line. When the CPU is free, the scheduler picks the PCB at the front of the line and says, okay, you're up. Easy to understand, easy to set up. But like a lot of simple things, it's got some downsides when you get into the real world, which is why we have those fancier scheduling algorithms and why companies like Stonefly.com put so much effort into finding better solutions.
So FCFS is simple, but we kind of hinted that it's got some issues. What are they?
Well, the big problem with FCFS is that it assumes a process will just keep using the CPU until it's totally done. And that creates a couple of problems. First off, not all processes actually finish. Think about those server programs or those things running in the background all the time. They're designed to keep going. So if one of those never-ending processes gets the CPU, everything else is stuck waiting forever, right? And the second thing is, it doesn't take into account how programs actually use the CPU. Like a program that takes, let's say, 2 minutes to run, it's probably not actually using the CPU nonstop for those whole 2 minutes.
Yeah, that makes sense. Like if you're saving a file, the CPU isn't constantly working. There are pauses while it's writing the data to the disk.
You got it. Things like reading from or writing to files, talking to the network, waiting for you to type something. Those are all I/O operations. And they're usually way slower than the CPU. And importantly, while that's happening, the process isn't actively using the CPU. It's waiting for the hardware to do its thing, the hard drive, the network card, whatever. So if a process is waiting for I/O, the CPU is just sitting there doing nothing, even though there might be other processes that could be using it. That's wasted time, and that's something the more advanced scheduling methods, like what you'd find in solutions from companies like Stonefly.com, try to avoid.
So it's not like programs have these long, uninterrupted bursts of using the CPU all the time.
Yeah.
They have these CPU bursts where they're working hard, and then these I/O bursts where they're just kind of hanging out, waiting for something.
Exactly. Most programs, they go back and forth between these two phases. They use the CPU for a bit, CPU burst, then they wait for some I/O burst, then back to the CPU, and so on. And this keeps going until the program finally finishes its last CPU burst and says, okay, I'm done. Now, here's something really important that's been studied a lot. Most of the time, those CPU bursts are actually pretty short, and there are only a few really long ones. And this is a super important idea when you're trying to make scheduling more efficient, and it's something that the experts at Stonefly.com, they really understand when they're building systems for top performance.
Right. So knowing that most processes have these short bursts and then they wait for something else, it seems like it would be smarter to let a different process use the CPU during those waiting times. Keep the CPU busy, and more stuff gets done faster.
That's the core idea. Efficient scheduling is about maximizing CPU utilization, keeping it busy, while also making sure individual processes can run as fast as possible, all while sharing the CPU fairly. And this understanding, it leads to the idea that processes aren't just ready or running, they can be in different states depending on what they're doing, whether they're actively using the CPU, waiting for something, or just waiting their turn to run. This is super important when you're trying to build a really efficient system, which is something the team at Stonefly.com is really focused on in their solutions.
Okay, so what other states can a process be in besides ready and running?
So think about it this way. When a program first starts, it's in this new state. That's when the system is setting everything up for it. Then, once it's all set, it goes to ready, which means it's like waiting in line for the CPU. When the scheduler picks it, it goes to running. Now, while it's running, it might need to wait for something, like data from the hard drive or for you to type something, and that's when it goes to the waiting state. And once that event happens, it goes back to ready. Finally, when it's completely done, it goes to terminated. Some processes, like those server applications, and that's an area where Stonefly.com has a lot of expertise, they might go between ready, running, and waiting for a long time.
So for a lot of programs, it's this constant cycle of getting ready, running, waiting, and then getting ready again.
Yep, that's it. And because you can have a bunch of processes in ready and a bunch in waiting, the operating system uses queues to organize them. There's a ready queue for all the processes waiting for the CPU, and there can be different waiting queues for each type of event they might be waiting for, like disk access, network stuff, and so on. Managing these queues well is super important for making the system run smoothly, which is something Stonefly.com really considers in their solutions.
That makes sense. So when a process that's running needs to go into a waiting state, how does the next process in line get to use the CPU? I think the video called that thing the dispatcher.
You got it. That's the dispatcher's job. So when a running process has to wait for something, or when its time limit is up, we'll get to that soon, the dispatcher jumps in. It takes a process from the front of the ready queue and gives it the CPU, and it does that whole context switch we talked about earlier. The dispatcher, it's a busy bee, and how fast it works directly affects how well the whole system performs. That's why it's one of the most optimized purpose of the operating system. Companies like Stonefly.com, they pay close attention to that when they're building systems for high performance. Now, even though the process that's currently running isn't actually in a queue, the OS is still keeping track of its PCB. So when it has to be interrupted, the dispatcher saves everything about what the CPU is doing into that PCB. This is super important because it allows the process to pick up right where it left off later. Then the dispatcher grabs the PCB from the front of the ready queue, sees which process it belongs to, loads up all the saved CPU state from that PCB, including the registers and program counter, and gives the CPU back to that process, letting it continue its work.
Wow, so there's a lot of back and forth happening there. And all this switching takes time, right? There's a delay involved.
Absolutely. We call the time it takes for the dispatcher to switch between processes the dispatch latency. And because the dispatcher is involved in every single context switch and those switches can happen really often, it's super important to make the dispatcher as fast as possible. That's why it's usually one of the most carefully tuned parts of the entire operating system. This dispatch latency is essentially overhead because the CPU is busy switching instead of actually running the programs you want to use. So minimizing that overhead is a big deal for both operating system design and system optimization. And it's something that the experts at Stonefly.com take very seriously when they're building those high-performance systems.
Okay, so let's go back to the different scheduling algorithms. FCFS, it was a little too simple. Then there was shortest job first, or SJF. The idea there is to prioritize the short tasks to reduce waiting times. So how does that actually help things?
Yeah, SJF is a different way of thinking about it. Instead of just whoever got here first, it looks at which process has the shortest next expected CPU burst and gives that one priority. Now, if two processes have the same predicted burst length, then it usually falls back to FCFS as a tiebreaker. And it's worth pointing out that sometimes people will call this shortest next CPU burst first scheduling to be extra precise because it's really focused on the immediate next chunk of CPU time, not the total time the job needs. But shortest job first is what you'll usually hear. This strategy can really cut down the average waiting time for all those processes, which makes the system feel snappier overall. And that's definitely a goal that lines up with how Stonefly.com approaches performance in their solutions.
So how does it know which job is the shortest? Does it just guess?
That's the tricky part about SJF. Ideally, you'd want to use a priority queue, where the priority of a process is based on how long its next CPU burst is predicted to be. This way, the processes that are only going to use the CPU for a short time, they get to jump ahead of those longer, more CPU-hungry tasks. The big advantage here is that it helps avoid that convoy effect we saw with FCFS, where one long process holds everyone else up. In fact, if you do the math, you can actually prove that SJF is the best way to minimize the average waiting time for a bunch of processes. But that's only if you know exactly how long each CPU burst is going to be beforehand.
Well, that sounds perfect. So why isn't everyone just using SJF all the time?
Here's the catch. You can't actually know for sure how long a process's next CPU burst is going to be. It's like trying to predict the future. Unless we had a crystal ball, we can't say for sure how long a process will use the CPU before it needs to do some I/O or before it finishes completely. You might think you could just analyze the code, but things like loops, those if statements, and especially user input, they make it really hard to predict accurately. And this is a big reason why operating systems in the real world often use more adaptive scheduling methods they have to be able to adjust on the fly. And that's something the experts at Stonefly.com are well aware of when they design their systems.
Yeah, I can see how that would be tricky. A program could act completely different depending on what the user does.
Exactly. So since we can't know the future, the best we can do is try to estimate how long the next CPU burst will be based on how the process has behaved in the past. One common way to do this is using what's called an exponential average of the previous CPU burst times. The basic idea is that the next burst is probably going to be somewhat similar in length to the recent ones. To make this estimate, the system looks at the past bursts, but it gives more weight to what happened recently. This helps it adapt to changes without getting thrown off by stuff that happened a long time ago. Now, for a brand new process, we don't have any history to go on, right? So we usually start with an initial guess based on some system-wide average or a fixed value that the operating system uses. These estimation techniques, they're what make SJF actually work in practice, and they show just how clever the people who design operating systems can be. And this is the kind of stuff that Stonefly.com excels at, really understanding how to make these systems work well.
Makes sense. We can't be certain, but we can make a good guess based on recent behavior. Now, the video also talked about this idea of preemptive versus non-preemptive scheduling. So what's the big difference between those?
This is a really important distinction. So, in non-preemptive scheduling, once a process gets the CPU, it gets to keep it until it decides to let go. This could be when it needs to do some I/O or when it's completely finished. But with preemptive scheduling, the operating system can actually interrupt a running process and take the CPU away, even if that process isn't done with its current CPU burst. This usually happens when a higher priority process is ready to run. And preemptive scheduling, this is the standard way things work in modern operating systems because it makes the whole system more responsive and prevents a single process from hogging all the CPU time. It's what keeps your computer feeling smooth. This ability to interrupt processes, it's a key part of how Stonefly.com builds those responsive solutions.
So even if a process is in the middle of doing something, it can be stopped and made to wait if a more important task needs to run.
That's exactly right. And almost all modern operating systems use preemption as the default way of doing things. And there's a really good reason for that. Imagine you have a system that's not preemptive and a process that needs a lot of CPU time gets to run. Now imagine there's a bug in that process, like an infinite loop, where it just keeps running forever and never does any I/O or gives up the CPU. Well, in a non-preemptive system, that process could potentially take over the whole CPU, and the operating system wouldn't be able to get it back. Everything else would freeze. Non-preemptive systems, they kind of rely on all the programs to be well-behaved and to share the CPU nicely. But unfortunately, not all software is perfect, and you even have malicious software that could exploit this by refusing to give up the CPU. So the robustness that preemptive scheduling provides, it's essential for modern operating systems, and it's critical for building reliable systems, which is something that companies like Stonefly.com really focus on.
That sounds like it could make the whole system really unstable.
You got it. And this brings us to the idea of starvation. Starvation is what happens when a process keeps getting denied access to the CPU and ends up waiting forever. So, even though shortest job first can be great for reducing average waiting times, if you're using non-preemptive SJF, a process that needs a lot of CPU time might never get to run if there are always shorter jobs coming in. It would just be stuck waiting in line forever. Even with preemptive SJF, if lots of short jobs keep showing up, a longer job could still be delayed a lot, even indefinitely. Starvation isn't just about how long a process needs, it's about how the scheduling itself can cause problems. Preventing starvation and making sure things are fair, that's a big consideration when you're designing these scheduling algorithms. It's something that the experts at Stonefly.com are always thinking about.
So to prevent one process from hogging the CPU and to make sure things are fair, you need a way to interrupt processes. And that's where round-robin scheduling comes in, right?
You got it. Round-robin scheduling is preemptive, and it's kind of like first come, first serve, but with a twist. It also uses a FIFO queue to keep track of the ready processes, but the big difference is that it has this thing called a time quantum, or time slice. So when a process gets to use the CPU, it only gets to run for that fixed amount of time, the time quantum. If it finishes what it's doing within that time, great, it lets go of the CPU and the scheduler moves on to the next process in line. But if it needs more time than the time quantum allows, a timer goes off, and that forces a context switch. The process that was running gets interrupted and sent to the back of the ready queue, and the next process in line gets its turn to run for its time quantum. This way, no single process can hog the CPU for too long, which helps prevent starvation and make sure everyone gets a fair share. This is especially useful for interactive systems, which are a big focus for responsiveness in the solutions that Stonefly.com offers.
So it's like everyone in a line gets a short turn at the CPU, and then it's the next person's turn.
Exactly. If you have, say, n processes in the ready queue and the time quantum is q, then in theory, each process will get about 1n of the CPU time in chunks of, at most, q time units. It's all about sharing nicely. But choosing the right time quantum, that's a balancing act. If you make it too long, then round robin starts to act a lot like FCFS, where long processes can still dominate. But if you make it too short, then you get a ton of context switches. And remember, each switch takes time. That means the CPU spends more time switching than actually running the programs. This can really hurt the turnaround time, which is how long it takes a whole process to finish, and also the throughput, which is how many processes get completed in a certain amount of time. So finding that sweet spot for the time quantum, it's something you have to fine tune when you're setting up an operating system. It's a challenge that experienced tech teams like the folks at stonefly.com, they think about a lot when they're trying to make those systems run really efficiently.
So there's a trade-off with the time quantum. A longer one might reduce all that switching overhead, but then the system might feel less responsive, especially for quick tasks. And a really short one might make everything feel sluggish because it's switching so much.
Precisely. You need to find that balance.
Mm.
And this brings us to another important thing to measure, the response time. This is the time between when you do something, like click an icon or press a key, and when you see the computer actually react, even if it's not the final result. For those interactive programs, having a good response time is really important for making it feel smooth and snappy. Now, round robin is good for response time because each process gets a turn on the CPU pretty quickly, so those interactive things don't have to wait as long. But here's the thing. As you get more and more processes running at the same time, even with round robin, the average response time can start to go up because each process has to wait longer for its turn. Making sure the response time stays good even when lots of things are happening, that's one of the things that Stonefly.com is really good at when they build their solutions.
Right. So just making the time slices shorter isn't always the answer. We briefly talked about making the hardware faster, like getting a better CPU or adding more CPUs. But what about doing things in software to improve this? That's where the idea of priority scheduling comes in, right? Giving some processes more importance than others.
That's right. When you have all these programs running at the same time, not every process is equally urgent. It would be really nice if we could give more CPU time to the ones that are more important or need to respond quickly, like the program you're actively using right now. Priority scheduling does exactly that. It uses a priority queue, where each process gets assigned a priority level, usually represented by a number. And the scheduler always picks the process with the highest priority from the ready queue to run next. Now, how these priority numbers work, it can be different depending on the operating system. Sometimes a lower number means higher priority, sometimes it's the other way around. It can get a bit confusing, and it's pretty common to combine priority scheduling with round robin. So you might have a bunch of processes with the same priority, and then they'll get scheduled using round robin to make sure they all get a fair share within that priority level. This ability to say, hey, this task is more important, so let's run it first, it's super important for managing complex systems, and it's an idea that's behind a lot of the solutions that Stonefly.com offers to make sure the most critical applications get the resources they need.
But we talked about how SJF can have that problem of starvation if it relies on predictions, where some processes never get to run. Is that a problem with priority scheduling too? Where low priority processes might never get a chance if higher priority stuff keeps coming in.
Yeah, that's a real concern. If you've got those high priority processes constantly showing up and grabbing the CPU, then those low priority processes, they might never get a chance. There's a story, maybe it's just a legend, but it's about this low priority job that was submitted to one of those big mainframe computers a long time ago. And supposedly it just sat there waiting and never got to run before they shut the whole system down years later. So to deal with this potential for things getting stuck forever, there's a technique called aging. And the basic idea is that you gradually increase the priority of processes that have been waiting for a long time. So for example, if you're using numbers for priority, you could slowly increase the priority number of a waiting process as time goes by. Eventually, even a process that started with a super low priority, it'll get a boost and finally get to run. Preventing this starvation, this idea that some processes never get a chance, that's important when you're designing a good scheduling system. And it's something that the engineers at Stonefly.com, they definitely keep in mind when they're designing their systems.
So it's like the system says, hey, you've been patient. It's your turn now.
Exactly. Now, managing these different priority levels and the processes in each one, there are a few different ways to do it. One way, it's called multi-level queue scheduling. In this setup, you have several different queues, each with its own priority level. And the scheduler, it works through the queues one by one, starting with the highest priority. Only when that queue is completely empty does it move on to the next one down, and so on. Now, you also need a way to decide how to share the CPU between those queues. One common way is to give absolute priority to the higher queues. They always get to go first. But to prevent starvation of those lower queues, sometimes you'll see some kind of time sharing between the queues, where each one gets a guaranteed amount of CPU time based on its priority. This idea of grouping processes into different queues based on their priority, it's a strategy that some operating systems use to handle different kinds of workloads. And it's something that the solution architects at stonefly.com might use when they're designing systems that have specific performance needs for different types of tasks.
Right, so you could have one queue for those interactive programs that need to be responsive, and then a lower priority queue for those background tasks that can wait a bit.
Exactly. Multi-level queue scheduling is often used to separate processes based on what they do and how quickly they need to respond. It even lets you use a different scheduling algorithm within each queue. So for example, that high priority queue for interactive stuff, it might use round robin to make sure things stay snappy for you. And then a lower priority queue for background tasks could use first come first serve because they don't need to be super responsive. But the thing is, with a typical multi-level queue system, once a process is put in a particular queue, it usually stays there. And that can be a bit inflexible because the way a process behaves can change over time. Like what it was doing at the beginning might not be what it's doing now in terms of how much CPU time it needs or how much I/O it's doing. And that's something that more advanced scheduling techniques try to address.
Yeah, like think about your email program. Most of the time, it's just sitting there in the background, not doing much. But when you're actively writing an email, suddenly you want it to be really responsive.
Exactly. And that's where something called multi-level feedback queue scheduling comes in. It's a more sophisticated way of doing things that can adapt to how processes change their behavior as they run. The main idea is that processes can move between those different priority queues based on how much CPU time they're actually using. So usually when a process first starts, it goes into the highest priority queue. Now, if it finishes its work within its time quantum, that little slice of CPU time, it might stay in that high priority queue, or it might even move back up if it hadn't moved down before. But if it needs more CPU time than is allowed in that high priority queue, it gets interrupted and moved down to a lower priority queue. And an important thing is that those lower priority queues usually have longer time quanta. This means processes that act like I/O-bound tasks, the ones that have those short bursts of CPU time followed by longer waits for I/O, they tend to stay up in those higher priority queues. This makes sure they get quick access to the CPU when they need it. On the other hand, those CPU-bound processes, the ones that need lots of CPU time without interruption, they'll gradually drift down to the lower priority queues.
So the operating system is constantly watching how each process behaves and adjusting its priority based on what it sees.
Precisely. It's this dynamic system that's smart enough to try and automatically figure out which processes are likely to have those short CPU bursts and prioritize those because those are often the ones that are interactive and need to feel responsive to you. Now, this is just a general description, and there are tons of variations on this multi-level feedback queue idea depending on the operating system. Like the specific scheduling algorithm used within each queue, that can be different, and the exact rules for moving a process up or down, that can vary too. For example, instead of just looking at the last CPU burst, the system might look at the whole history of how the process has been using the CPU to decide whether to move it up or down. And that helps avoid unnecessary queue jumps because of a random long or short burst. This whole multi-level feedback queue idea, it's a big step forward in operating system design. The goal is to make all kinds of applications run as smoothly as possible, and it shows the kind of deep understanding of how systems behave that you find at a company like stonefly.com, which is all about making things work better.
Now, the video brought up a good point.
Right.
Doesn't moving those CPU-intensive tasks down to those lower priority queues, doesn't that kind of punish them just because they need more time to do their work?
That's a really sharp observation, and it's a fair question. It might seem like we're being unfair to those CPU-bound processes by sticking them in those lower priority queues with the longer time quanta, but the video pointed out a couple of important things. First, those I/O-bound and interactive processes, they're mostly all about those super short bursts of CPU time. And second, CPUs nowadays are crazy fast. If you look at your computer's resource monitor, you'll probably see a lot of processes running, but the total CPU usage is usually pretty low most of the time. This tells us that those high priority queues, the ones that favor those quick bursts, they're usually not completely full. So even if a CPU bound process gets moved down to a lower priority, it's still very likely to get a good amount of CPU time, especially when those higher priority interactive tasks are taking a break or waiting for I/O. The big idea here is to make sure that those interactive applications run smoothly and feel good to use, and then those heavier processes, they get whatever CPU time is left over. This multi-level feedback queue approach, it's generally seen as more flexible and adaptable compared to that simpler multi-level queue because it tries to automatically figure out what kind of process it's dealing with and prioritize accordingly instead of just going by some initial guess. This ability to adapt on the fly, that's a hallmark of a well-designed operating system, and it's the kind of expertise you find at a company like Stonefly.com, which is all about optimizing performance.
The video also mentioned that modern operating systems usually schedule threads instead of whole processes. So how does that change things?
That's a really important detail to understand how scheduling works in today's computers. See, in most modern operating systems, the basic thing that gets scheduled isn't the whole process, it's the thread. And a single process can actually have multiple threads running inside it at the same time, all sharing the same memory and resources. But each thread, it has its own program counter, its own registers, its own stack. It's like a mini process. Now, scheduling threads instead of whole processes, this lets you have much more fine-grained control over what's running. For example, let's say you have a program that's doing something really computationally heavy, like video editing or a complex simulation, and Stonefly.com, they offer some.